All right, today we are diving into one of the most powerful tools in any electronics toolkit, mesh current analysis. It's a really elegant way to solve circuits that at first glance might look completely impossible to figure out. So just take a look at this. You've got multiple power sources, you've got resistors that are shared between different paths. I mean, where would you even start? If you try to just use basic Ohm's law on every single piece, you're going to end up with a tangled mess of equations so fast. There's got to be a better way, right?
So that's our challenge, solving these tricky, complex circuits. Let's really nail down what the problem is before we jump into the amazing solution.
Yeah, here's the real issue. It's those shared components. As soon as you have parts that belong to more than one loop, the standard ways of doing things can create just a huge number of simultaneous equations. It is a genuine headache to track everything. We need a method that simplifies the problem from the get-go.
And that, my friends, brings us to the hero of the day, mesh current analysis. This is the technique that was literally designed to bring some beautiful order to this exact kind of circuit chaos.
Okay, first things first, we need a key definition. What in the world is a mesh? Well, imagine a window with, say, 4 panes of glass. A mesh is just one of those individual panes. It's a loop in the circuit that doesn't have any other smaller loops tucked inside of it. Being able to spot these is step 0. And here is the magic trick. This is the core idea of the whole thing. Instead of trying to track the actual current flowing through every single wire, we just imagine one single unified current circulating around in each mesh. This little bit of genius, which is based on Kirchhoff's voltage law, dramatically, and I mean dramatically, simplifies the math we have to do. And you know the best part? This powerful technique isn't some abstract art form you have to master over years. Nope, it's a straightforward, repeatable 4-step recipe. Let's break it down right now. So here it is. This is our roadmap. Step 1, we're going to assign a current to each mesh. Step 2, we'll use Kirchhoff's voltage law to write one equation for each of those loops. 3, we solve those equations to find our mesh currents. And then finally, step 4, we use those answers to figure out the real current flowing through every single component. Simple, clean, and incredibly effective. Theory is great and all, but let's be real. Seeing is believing. The best way to understand this is to actually do it. So let's apply this 4-step method to that tricky circuit we started with. Okay, here's our circuit again, but this time we've got some actual values to plug in. We have a 10-volt source on the left, a 20-volt source on the right, and 3 resistors in between. Now we can really get our hands dirty. Step 1, and honestly, this is the easy part. We just identify our 2 meshes, or our 2 loops, and we draw in our imaginary circulating currents. We'll call the one on the left I1, and the one on the right I2. And just by convention, we almost always draw them going clockwise to keep things consistent. Now for step 2, let's apply Kirchhoff's voltage law to that first loop. The law says that the voltage supplied by the battery, that's 10 volts, has to equal the voltage dropped by the resistors. So the drop across the first resistor is simple. It's just I1 times 10 ohms. But here's the crucial parts. Look at that middle resistor. The actual current going through it is a mix of both our mesh currents, right? It's I1 going down, but I2 is going up. So the net current is I1 minus I2, and the voltage drop is that current times 30 ohms. We do a little bit of algebra to clean that up, and boom! There it is, our first clean equation. This single line represents the entire voltage relationship for that first mesh. 1 down, 1 to go. Okay, let's do the same thing for loop 2. Now, notice here we write negative 20 volts. Why? Because look at our clockwise current I2. As it goes around the loop, it enters the negative terminal of that battery first. That's a key convention. The rest is similar. We have the voltage drop across the 20 ohm resistor, and then the drop across that shared resistor, which from I2's perspective is I2 minus I1 times 30 ohms. And once again, we simplify it down and we get our second clean equation. So this is the moment. We have 2 distinct equations and only 2 unknown variables, I1 and I2. We have successfully translated the entire circuit into a solvable math problem. This brings us right to step 3. All the physics, all the circuit theory, it's done. Now it's purely a matter of solving this system of simultaneous equations. You can use whatever method you like, substitution, matrices, an online calculator, it all works. So after we solve it, these are the values we get for our mesh currents. Now wait a second, they're both negative. don't let that throw you. This is actually one of the coolest parts of this whole process. It doesn't mean we did anything wrong. It just means the actual direction of the current is opposite to our initial clockwise guess. The math automatically corrected us. How amazing is that? And finally, we get to step 4, the grand finale. We use our solved mesh currents to find the real current in each individual branch. The current through that first resistor is just I1, but flowing counterclockwise. Same for the second resistor. And the current through that shared middle resistor? It's the difference between them, which comes out to 0.286 amps flowing downwards. And just like that, we have completely solved it.
So we went from a really confusing diagram to having precise, concrete answers. Let's just take a moment to recap why this method is so powerful and so important.
So why does this matter so much? Well, mesh analysis gives us a reliable, step-by-step process that just works. It turns what could be a jumble of wires and guesses into a clean, organized set of equations. And it's a direct, practical application of Kirchhoff's voltage law. Honestly, for anyone going into electronics or engineering, this isn't just a trick, it's a foundational skill. You know, I think this quote just sums it up perfectly. It's not just about crunching numbers, it's a way of thinking. It's a method for taking something that looks totally chaotic and turning it into a structured, solvable, and even elegant puzzle. And that kind of leaves us with a final thought to chew on, this whole idea of breaking down a big, messy, complicated system into smaller, more manageable interacting loops. Where else could we apply that thinking? You could think about supply chains or social networks, or maybe even just managing the projects in your own life. It's a really powerful way to look at the world. Thanks for joining me.